Welcome to the TOEFL listening section. In this part, you will hear one or more conversations in an academic or campus context, such as a discussion between a student and a professor, or between two students. You may take notes while listening. Listen to part of a conversation. You will hear it only once, so listen carefully. After the conversation, you will answer questions about what you heard. Some questions will ask you about main ideas and details. Others will ask about implied meaning, speaker attitude, or how ideas relate to one another. Use both what is stated and what is implied to answer.
Good afternoon, Dr. Morales. Thanks for meeting me during office hours. I wanted to discuss my project on smart fabric development and get your input on experimental design.
Good afternoon, James. I read your proposal summary. Let us talk specifics. What aspect of smart fabric development are you focusing on? Sensing integration or power management?
Primarily sensing integration. I want to weave conductive yarns into a textile to monitor heart rate and skin temperature. But I am concerned about signal quality and washability.
Those are common challenges. When you say conductive yarns, which type are you planning to use? Silver-coated fibers, graphene-enhanced yarns, or intrinsically conductive polymers?
I was thinking silver-coated nylon for the leads and PEDOTPSS coating for stretchable sensor areas. I read that silver offers low resistance but has durability issues without protection.
That is true. Silver-coated fibers have excellent conductivity, but they oxidize and abrade. PEDOTPSS is flexible and can be printed, but its conductivity is lower. A hybrid approach often works, using silver traces for interconnects and PEDOTPSS at the sensor interface to maintain stretchability.
Hybrid approach makes sense. For fabrication, I was considering embroidery for placement of sensors and a woven grid for interconnects. Is that feasible at prototype scale?
Yes. Embroidery allows precise placement and is compatible with industrial textile processes. Woven grids provide stable mechanical support. You must consider contact resistance, where embroidered sensors meet woven leads. Use overlap stitches and conductive adhesive to lower contact impedance.
What about printed electronics on fabric? Screen printing conductive ink seems simpler for planar sensors.
Printed electronics are good for flat regions. Silver nanoparticle inks and graphene inks are options. Silver inks give low sheet resistance but require sintering, which can be challenging on textile substrates. Thermal sintering may damage fibers. Photonic sintering or room temperature chemical sintering can help.
I had not considered sintering constraints. For the sensor itself, I want to measure both ECG and skin temperature. Should I separate sensor modalities into different textile layers?
Separation can reduce crosstalk. Place ECG electrodes on an inner layer with direct skin contact and temperature sensors in a nearby layer with thermal contact through a breathable window. Keep signal traces short to minimize noise and use shielding where necessary.
You mentioned shielding. How do you implement shielding in smart garments without losing breathability?
We use narrow conductive meshes or pattern shielding using conductive yarns woven into non-critical areas. Another approach is to integrate an antenna textile for wireless telemetry that also acts as partial shielding. The key is strategic placement to avoid covering large breathable zones.
Power supply is another concern. Small batteries add stiffness. Are energy harvesting methods viable for continuous monitoring?
Energy harvesting like thermoelectric layers or piezoelectric fibers can supplement power but rarely provide enough for continuous high data rate streaming. A hybrid system with a small flexible battery and intermittent wireless transmission conserves energy. Consider duty cycling the sensors and using local processing on a textile-mounted module.
Regarding user comfort, I worry about hand and drape. How do you maintain traditional textile hand after integrating electronics?
Minimize stiff components and distribute electronics over larger areas. Use encapsulation films only where needed and select thin, flexible modules. Textile-based antennas and embroidered interconnects preserve drape better than laminated circuit boards.
You said encapsulation. What materials are common for encapsulating conductive elements to ensure washability?
We often use polydimethylsiloxane, or PDMS, in polyurethane coatings for flexible encapsulation. They protect conductive yarns and maintain signal integrity during washing cycles.
So PDMS is flexible enough for stretch areas. How do you test washability in the lab to simulate real use?
Use standardized washing tests. For textiles, we follow ISO 6330 style protocols to simulate domestic laundering. Evaluate electrical resistance after multiple cycles and run bending and abrasion tests to simulate wear.
I will include washability testing in my methods. For signal integrity, you mentioned short traces. Is impedance matching important in textile antennas and telemetry?
Impedance matching is important for antennas to ensure efficient radiation. For sensing traces, low DC resistance and stable contact resistance matter more. Use 4-point measurements to characterize contact impedance and resistance per meter.
What about biocompatibility and skin irritation? Some encapsulants and conductive coatings might cause reactions.
That is a valid concern. Select materials with proven biocompatibility and perform cytotoxicity tests for skin contacting regions. Use textile substrates like cotton or polyester that are comfortable, and use barrier layers between electronics and skin where needed.
Could you recommend a small case study I can replicate for my thesis? Preferably something with both sensors and real-world application.
Design a prototype monitoring garment for firefighters that integrates gas sensors and heart rate monitoring, that allows you to test robust encapsulation, rapid signal acquisition, and harsh environment durability. Alternatively, an athletic shirt measuring EMG and temperature is useful for biomechanics studies.
A firefighter garment sounds challenging but impactful. For the gas sensors, would you embed electrochemical sensors or use colorimetric detection?
Electrochemical sensors are better for continuous monitoring and digital readout. Colorimetric patches are low cost but require optical reading and are single use. For integration with textiles, electrochemical sensors with microfluidic sampling channels can be embedded in a protective pocket.
Thank you, this is very helpful. For my timeline, I will prototype a small ECG and temperature module with woven interconnects and PDMS encapsulation, and run 10 wash cycles and bend tests.
That is a solid plan. Also, document manufacturing steps carefully and note any changes in textile feel and breathability. We can discuss early results next week and refine materials based on performance.
I appreciate your guidance. I will prepare the materials list and initial procedures and email them to you. Thanks again.
You are welcome, James. I look forward to seeing your prototype in data.
Listen again to part of the conversation, then answer the question.
We often use polydimethylsiloxane, or PDMS, and polyurethane coatings for flexible encapsulation. They protect conductive yarns and maintain signal integrity during washing cycles.
This concludes the conversation portion. For more TOEFL practice tests and study materials, visit spinta.org.